So now that you've gone and graphed those library of functions and have an idea of what their basic shapes are, there is a handout loaded into the module that has all that information about those basic shapes. So after you've done your task, you can definitely download that and print that out for your own records. So what we're going to talk about now are piecewise defined functions. And what this does is this takes parts of different functions and puts them together into a single function. So it's a function that's defined in separate pieces. So what you're going to see on example 1 is an example of a piecewise defined function. So we have p of x, and that's equal to, and you see this brace, and then you're going to see 3 different lines. So 5, and that's if x is less than negative 3. We also see x squared minus 4 if negative 3 is less than or equal to x is less than or equal to 3. We have it's equal to 2x plus 1 if x is greater than 3. So we have 3 different pieces to this graph. And you'll notice that this part about the if is what's defining our input value. So it's telling me which input values I can use. This is still a function. So that means if you plug in a number, one number, you should only be plugging it into one of the pieces in order to get a single output. If you plugged it into all 3 pieces, you get 3 outputs and it's not a function. So one input, one output. You just have to decide which piece you're plugging it into. So to help us out in terms of that, what I'm going to do is I'm going to label these as Roman numeral 1, Roman numeral 2, and Roman numeral 3. And this just so we can discuss them. That's the only reason they're numbered. So we're going to evaluate this piecewise function. And the first value we want to find is where this function exists at negative 5. So what I have to determine is where negative 5 falls in these restrictions on the domain. Well, negative 5 is less than negative 3. It is not in this interval, and it's definitely not bigger than 3. So negative 5 falls into piece 1. So we're going to use piece 1. So what it says, if we plug in a negative 5, is we output a 5. So there's not really any work to do with that. We're just recognizing which piece to plug it into. Part B on that one says, well, what about p of negative 3? So which piece are we going to use for negative 3? So again, I take my input, go figure out where it falls in terms of input values. It's not less than a negative 3. It's equal to a negative 3. So because our x input is equal to that negative 3, we're going to use piece 2. So that means that p of negative 3 would be equal to negative 3 squared minus 4. Well, that's 9 minus 4, which comes out to be 5. And it's a fluke, essentially, that 5 is the same as this 5. It just means that these 2 pieces meet up, and we'll talk more about that once we start graphing them. So part C says p of negative 2. So p of negative 2. Negative 2. So again, our job is to figure out which piece we're plugging that into. So when I take a look at negative 2 is between negative 3 and 3 on the number line. So that tells me that, again, we'll use piece 2. So we're going to use piece 2, and it's going to be equal to that negative 2 being squared minus 4. Well, negative 2 squared is a positive 4, minus 4 is 0. So notice we get a different value finally. Part D says, what about p of 0? So again, p of 0. 0 falls between negative 3 and 3. So again, we're using piece 2. And that's going to be equal to 0 squared minus 4, which gives me negative 4. So we could be building little x and y tables to help us graph here if we were graphing this one. Part E is asking us to find p of 3. So p of 3, again, we're paying attention to where those equal to's are. And this equal to is on this piece. So this is when x is equal to 3. We'll use piece 2 again. And we find out that it's equal to 3 squared minus 4. 3 squared minus 4, sorry about that. That would be 9 minus 4, which is equal to 5 again. And then finally, the final one says F. We want to find p of 5. So 5 as an input is greater than 3. So for the first time, we're going to use our third piece down here. So we'll use piece 3. And we're plugging in 5. So it'd be 2 times 5. Plus 1, that's 10 plus 1, which is 11. So we've evaluated the function at each of these different pieces. But again, I only plugged each of these inputs into one of the different pieces in order to graph that, or sorry, in order to evaluate it. Now we're going to go graph one. So we're going to go pretty slow with this. It's our first example. Especially if you've never done this kind of thing before. There's some analysis. I want you to think about it before you just blindly come in and start trying to graph things. So example 2. It says f of x is equal to, and we have two pieces, in x minus 1, and this is if x is less than or equal to 0. It would be equal to the square root of x if x is greater than 0. So you're going to notice that this is one of your library of functions that we already talked about in this section. So what I'm going to do first, before we do anything else, is going to make a couple of notes to myself. The boundary number is the x value where the graph goes from one piece to another piece, and they tell you that information. So for us, our boundary number is at 0 because that's where the difference is between our pieces. So for us, it's our boundary number and it's 0. And I like to identify that because it's important when I go to start building my tables. Because this piece is less than 0, this is going to be our left side of our picture when we're all done. And what we're going to notice is that x minus 1 is a line. It's a line with a positive slope. So the left side needs to be a line, and it has a positive slope, so it should go up. We could do a lot more with it, but no, we will in just a second. But I like to do that analysis first. Okay, this is the right side, and I know it's the right side because it's greater than 0. And this is that square root function from our library of functions, and we know that it's a curve, and it looks something like that. So that's my little mini analysis of what's going on. So when I'm all done, I can sit back and say, oh, yeah, it came out exactly like we said. I'm going to do them one step at a time. If you have a lot of experience with this, you won't need to build these tables, but if you've never built the tables before, I strongly urge you to do that. So our left side was y equal to x minus 1. Notice I'm taking out the f of x and plugging in a y because you're more familiar with that. It feels more comfortable. Now we know it's a line, so we're just going to build an xy table, and we're going to only use 2 points because it's a line. That's all we need. What I'm going to do, though, is plug in that boundary number as my first piece. So my first number I'm going to pick is the boundary number, and that's true no matter what I'm doing with these piecewise functions. I'm going to make a note to myself that because this has the equal to on it, that this is going to be closed. And just kind of follow along. You'll see why when we're all done. So when we plug in 0, 0 minus 1 is negative 1. Well, now I need another point. And because it's the left side, I need to go to the left of 0. So I'm going to plug in negative 1. So that would be negative 1 minus 1, which is negative 2. And usually once I finish analyzing the piece, I'm going to go graph it because it works best for me. You don't have to, of course, but this is the way I like to. Okay, so we have the point 0, negative 1. It is closed. And then we also have the point negative 1, negative 2. It's also closed because we're now picking anything to the left of it. It's going to be closed. I'm going to draw that in. And again, I'm going to remember it's the left side. So I'm going to start at the boundary number and go to the left. Here's the left piece. Okay, let's take a look at that right side. So we'll have y is equal to the square root of x. So we have x and y. And because it's a curve, I'm going to make sure I plot quite a few more points, not just 2, 3 or 4, right? Again, I'm going to plug in the boundary number because I need to know what this is doing as we transition from one piece to the next. And if I start at 1, I don't know what's going on between 0 and 1. So I have to use that boundary number. However, because the inequality says it's greater than 0, we're going to use this as an open circle. So I'm going to make a note to myself that it's open. If we plug in 0, square root of 0 is 0. Plug in 1, I'm picking numbers to the right because we're on the right side of the picture. Square root of 1 is 1. I could plug in 2, but square root of 2 is a decimal, and I don't like flat decimals. So I'm going to skip all the way up to 4 because it's going to be square root of 4. The square root of 4 is 2. And if I needed one more point, I'd plug in 9, next perfect square, and get a 3. So at 0, 0, we're going to have an open circle. We have point at 1, 1, 4, 2, and then 5, 6, 7, 8, 9, 3. And sure enough, there's the curve that I'm expecting to see. And there's your first piecewise graph. Now, once you have that piecewise graph, what I would then recommend doing is answering the questions. And what we want to know about are the domain, the range, the intercepts, and then it's whether or not it's continuous, which is new to us. So for us, our domain is going to go from negative infinity to infinity. So the arrow on the left, the arrow on the right. Notice it is still a function. It passes that vertical line test, right? Even right here, the graph is here, not up here because of that open circle. So it passes the vertical line test, which means it's a function. So that's great. The range is a little goofy because we have this break. So there's nothing in this area. So we're going to go from negative infinity to negative 1 with a bracket because it is closed. And then we'll union that from 0 to infinity. So the bottom of the graph is down here at negative infinity. It stops at negative 1. And then we pick it up again at 0 with a parenthesis to exclude the 0. going on towards infinity. We do have an intercept. We have a y-intercept at 0, -1. We do not have an x-intercept, so no x-intercept. In other words, it is not touching or crossing the x-axis. This open circle is not an intercept. This one is not continuous. And what does that mean? Well, continuous means that you can trace it without lifting your pencil from left to right. If I were trying to trace this, I wouldn't be able to go from here to here without lifting off my marker. So it is not continuous. And there's your first piece by function.